Hello everyone, I am Divyaranjan, PhD scholar. So welcome you all to the demonstration of Rheometer. So before going to the main experiment, so here I will tell the basic component of this Rheometer, right? So this Rheometer of Anton Power Company and this model is MCR102E. So basically this Rheometer has one compressor, it is air compressor, and for lubrication air is the main component, but there is no oil, and this is where the software is installed desktop, and this is the main part. This is the Rheometer. So where actually this is the head of the Rheometer, where the probe the compressor is giving power to this head. There is a motor, it is operated by the compressor and rotation is happening, on which principle we are applying strain to our sample and applying also stress. So this is the main probe of the sample, probe of the Rheometer, and this probe it is of two part. See, this is the probe and this part is the plate. So as sir told in the lecture, there are two kinds of probes are there. Cone, one probe, two plate. One is cone plate and another is parallel plate. So whenever we are talking about cone plate and parallel plate, you might have one doubt, what is cone plate? Cone plate is, there is little bit angle. Sir has shown you one angle like this, so it is not visible, there is no significant angle is there. This is cone plate and this is parallel plate. So the cone plate, it will be having 1 to 2 degree angle, which is very less. So you may not it may not be visible, but there is 1 to 2 degree angle. And this is parallel plate, it is already attached to the probe. So we can attach this parallel plate, this plate with the probe, and this is the screw here. So one thing is that where we will use this parallel plate and this cone plate. Okay, so the liquid which is of very viscous in nature, like you can take milk or honey. So whenever we are applying this material, it will be spreading through a large diameter. So at that time, so it will be spreading through a large diameter, and if it is of very liquid in nature, its viscosity is very less, so the material should be trapped inside this plate, both plate, so that there will be operation will be happening, shear stress and shear rate both will be applied and will get result. If it is less viscous, then there is chances of slipping out of this material, because there should be something between these two plate, if so that we will be applying stress. If there is nothing, so what happen, if less viscous material will be there, due to this minute angle it will be trapped. Understood? There is angle. Okay, so angle, there will be some little bit space, so it will be accommodated, the sample will be accommodated in that space and it will give result. So that is the basic difference between cone plate, using of cone plate and parallel plate, right? So coming to diameter, small diameters are there, it is having 50 diameter and it is also having 50 diameter. So the in terms of diameter, for each parallel plate and cone plate, two diameters are there. One is 25 mm, another is 55 mm. So 25 mm are small. So when you will use 25 mm dia plate, when you will use 50 mm dia, so there is difference. As I told, less viscous sample will be spreading more. So for less viscous sample, since it is spreading more, so we can use this higher dia, because whenever I am pouring this less viscous sample here, it will be spreading over more diameter. So due to the spreading of more diameter, we have to get a more surface area plate. So due to that, we are using higher diameter plate, that is 50 mm. But whenever sample is more viscous, like your mayonnaise and something dough kind of thing, so if you are pouring the sample, due to more elastic in nature, it will stay like that in a heap position. So for that purpose, so we are using small diameter sample, so small diameter plate, and this small diameter you can use that large diameter, but this large diameter plate you will make your sample wastage, because it will stay within very less diameter of area. Why you will use more die plate? Okay, so that is the basic thing, the difference between this cone plate and parallel plate, and larger die plate and smaller die plate. And the main actually prerequisite while you are operating the plate, these are kept inside this packet, right? So this is a Ziploc packet. So whenever you are taking out any probe for any experiment purpose, and you are keep it in the right packet, because there is your mark is there, right? But whenever you are keeping it any other, because it is not noticeable, small minute angle, if you are in mistakenly you are putting this cone plate inside parallel plate, then there will be chances of like more confusion and all. So this is the basic part. Here we are going to pour our sample, and the sample, and we will be lowering the plate and this plate, and we will set our parameter over here, and that is shear strain and shear rate, and it will give a different kind of plot. Okay, so the basic thing is that, so the first test what we are going to study is the flow curve. So what is the flow curve actually? The flow curve is mainly, curve means the fitting of different data point, and the flow curve is actually representing the flow behavior. The basic thing of the rheology what we are talking about is the flow. Okay, so how the flow is actually behaving. Suppose this is the winter season, we are applying some cold cream on our skin. Okay, so simply we are applying some cold cream, it is not happening of its own, like it is not spreading, we have to apply some stress, okay, so that it will flow. So whenever we are packaging that cold cream, we are packaging in such a manner that it is not getting spreaded, because it should be in most elastic manner. But whenever we are pouring, we are taking it outside, applying stress on the packet, and it will come outside. So we are applying stress to come outside. So what is happening there? We are changing the properties, little bit elastic to little bit viscous, right? So little bit elastic to little bit viscous by applying stress. So this is the daily, day-to-day time. Suppose you are eating jam. So jam is inside the packet. It is having more elastic, okay, nature, because we are keeping in such a manner that will control wave of ration, so that we are putting without disturbing more. Whenever we are taking out this jam, we need to spread the jam over the bread. Okay, so for that purpose we need to apply some stress. So there are different kind of things, like if someone is using honey to disturb the honey, you need not require more force, because whenever you are applying, automatically it will be spreaded. So that what Sir was telling in the lecturer, that what is that, viscoelastic solid and viscoelastic liquid. So other
viscoelastic solid, whereas honey is viscoelastic
liquid. So that is the main thing. So the thing is that, so our basic thing is, it is the flow curve, right? So these are the operation, because previously I said everything, because it will take time. So the basic, what I did not do much of work, because I started the compressor, and the compression will give the power. Here rotor unit is there, the rotor unit will rotate the probe and plate assembly, right? This probe will rotate, and it will give you the apply the shear stress and strain. So now what I am going to do, I will apply the sample over here, right?
Shear is acting upward, no, in the plate.
No.
And downward. Shear is acting upward.
Yes, we are applying the sample here, over here, and the plate will go downward, and the plate will be moving. So we are applying shear, okay, in terms of angular moment. Okay, the two things are there. Okay, this is in linear, okay, and whatever you are puffing, we are giving angular movement. Okay, so that is the thing. So anyway, so this is the mayonnaise we have purchased from market. So we are directly pouring it. You can pour actually some more amount, okay, because in between the plate there should be something. I told, actually there is chance when we are pressing the plate, slippage will occur. I'll show you now. Due to, so like this spilling will occur, it will come outside. So we can take the extra material, no issue. But if you are putting less, there will be less material in between the plate. Okay, sufficient material should be in between the plate. So these are the like prerequisites. By doing several times the experiment, your hands will be free, and you will be, there will be no confusion in that, right? So the thing is that, so the sample I applied over here, you see I actually applied, so it is you can see it from outside, you can say that it's viscoelastic in solid, right? So I am taking the plate down, see, so when their pressing is happening, so there will be peeling, you see material will come this side, and this gap is adjustable. One thing, this gap, suppose I am putting a sample which means this gap here I have adjusted the gap 0.5 mm. In parallel plate you can adjust the gap, but in cone plate you can't adjust. The minimum thing is in cone plate is 0.1 mm, 0.1, but here you can adjust the gap according to the sample size. Suppose I am keeping some what is that cheese, okay, the cheese it can't be compressed to very close, okay, so this it needs some more space. So in that cheese sample we can increase the gap. So this is the means rod through which we can remove the extra thing that got spilled outside. So in this way we have tissue. So this is the thing. Okay, so and one thing is that I applied the sample over there, over the plate, and you should not disturb more, because if you are disturbing more then you are disturbing by yourself. Okay, you have to put the sample at zero condition so that the equipment will give you the data what the equipment will judge, because you will disturb the sample. So the sample is already before the operation, has been already applied with different stress and strain kind of thing, so it should not be there, right? So I applied the sample. So here trim, so this operation is a trimming operation, right? So after trimming this is continue, right? Give some beep sound. Okay, now the thing is that operation. So here I am going this flow curve. So whenever I am opening this flow curve test, I am opening the test, so it will give you to put the name, like the folder you will create. In that folder you will run several experiment, different sample. So you can put the sample name. Anything you can put the folder. Okay, so demonstration. Okay, so now here we have to put different parameter like shear stress and strain. So this thing because this plate is applying the shear strain and stress, so here these are the step like set value, diagram, flow curve, and regressions are told you. Various plots are there, Bingham model and power law model. So these are power law model and Herschel-Buckley model. These are the model, because one is the experimental data, another is the model data. What we are doing, we are fitting the experimental data through a model and we are checking the accuracy, right? So here the software is designed in such a way that both the model data it will give as well as the experimental data. So see here only we are putting the shear rate value, shear stress and shear rate. The equipment will tell you are giving one value shear rate. So the shear rate, the equipment will apply, the probe will apply the shear stress. So it will give your shear stress versus shear strain, your viscosity graph. So basically you can take it from 1 to 100, right? Shear rate. The unit is 1 by s, second. So right, after putting the sample, after I have already set the parameter here, you see what is showing here, time setting, we are taking 100 data point, 100 data point will be there, and point duration for each data point 2 seconds, and interval duration is 200 seconds. Okay, so that number data point it will come. So basically the thing is that if you are taking more data point, it is of no use, right? You have to see the trend and the plot. Okay, because all the play here is happening, structure. We don't know when the structure will break, but we are giving some optimum value, right? If you are giving some infinite value, suppose some more value I am giving here, so what will happen? The structure will be breaking down and it will give uneven data. In this way it will be fluctuating, which is not required. Whatever you are doing in your daily life, whatever you are doing it has some optimum range. Okay, if you are crossing this optimum range, the structure will be breaking down, then nothing will, it will give some abrupt data, okay, which is of no use, and you cannot study, you cannot interpret that also, right? So this basic is 1 to 100 shear rate we are giving. Now we are starting it. So I told you the main folder I created, that is the main folder, okay. In between that you can run several experiments. So here I am giving suppose sample 1. So now I am starting the experiment. This is continue. So here some like according to the room temperature, here I have set 25, right? And here there is actual 25 and actual 25. So there is some tolerance time, right? So this tolerance time, it will be matching this system temperature and this temperature. When it will be exactly 25 and will come, it will start the experiment, right? And one thing, this is the Peltier plate, you know, the Peltier effect, the temperature cooling and heating will be adjusted, right? So this is the plate. If I will increase, suppose someone wants to conduct the temperature at 30 degree, 40 degree, so we can set the temperature over here, and according to the temperature your things will run.
So the gap is 0.5 mm because it is viscoelastic solid.
Hmm.
So what will be the gap if we use viscoelastic?
No, actually it depends upon product to product, right? I told you, if you are going to put cheese, okay, if you would have, if I I'm coming to you, this is the graph, this is two things, this is shear stress versus shear rate, this is shear stress versus shear rate, and this is viscosity versus shear rate, okay. This operation will go on, and here it is showing 4 data point, right? Here it will go up to 100 number of data point, right? So it will give the curve, total the curve will come, after that we will discuss. So your question, I am coming to you, because it depends upon the size, right? If I would have put here 1 mm, so there won't be any issue, right? But whenever you are running it for several time, according to your experience you can tell, okay, because mayonnaise it's there, so it can be compressed very little gap, okay. So that's why I have said here 0.5. If suppose cheese you are putting here, you can, by doing the experiment you can see whether 1 mm, other 2 mm, because here there is sensor, okay, and there is normal force, you see N, okay. If the normal force will not be in range, that will be in the bearable mode, okay. So the equipment will give some beep sound. Actually here some normal force, that is not actual normal, that is apparent. Apparent means the things is there, something is there, and you are applying some force, you are applying some stress, but the material it has also its own strength, so it will be giving some back thing. Suppose in a pipe you are applying some water, okay, so water molecule is going, but due to among this water molecule there is also striking is happening, so it will give some back pressure, right? So in this way you can see some back force is being applied. So if you are applying a material which is like cheese you are giving, and it should require more gap, but you are giving less gap, what will happen? It will give some upthrust, right? And the equipment it will give you some beep sound, so that it is not in the, like you have set more very less gap, but it needs more gap, so that will be more normal force, right? So due to that the equipment will tell you, on basis of that you can adjust the gap, okay. So here 62 data point completed, right? So 62 data point completed. So here when 100 data point will be completed, the experiment will be over, right? So you see it's running, is the shear stress versus shear rate, okay. So and this is the diagram, and this is the table. You see the table also, you will take the table and you will plot it, okay, and any like Excel and Origin you will take and you will plot it, you will get the data. Here it is directly showing you the diagram, okay. You can this is diagram, it is showing according to giving some arrow mark for each data point, right? This arrow mark it is giving, but it is like if whenever you will be plotting it on Origin or any Excel, so it will be giving you a smooth curve, okay.
So
No, it will not show deviation.
Like I have done this test. In that test, deviation was there.
Which sample was it?
I used carrot juice with some means different type of samples.
Carrot
It
juice.
depends upon.
I don't know if there will be some particle inside this. Okay, that carrot juice, that's some carrot that pomace. It should not be like that. Only total concentrate sample will be there. But if due to that, actually something might happen. But whatever I have run actually in this thing, there won't be any kind of like abrupt kind of things.
Like in my case, it was there. So.
But that is not required at all. That is unwanted.
Like I wanted the reason. I asked the.
No, that is maybe depends upon the sample kind of thing actually.
Main concern.
Main concern means what is the thing, like I have given the mayonnaise, okay, so there should be not suppose you are preparing some carrot juice, you are telling in that some pomace will be there, so it should be smooth because that will be yes, that's the main thing actually. That should not the part, there should not be any granular kind of thing in between, okay. So if you are applying, it should be properly homogeneous, right? Unless it will give off some abrupt or some time it will be increasing, decreasing, falling and dropping, so in this way, but it should be smooth only. You see, when you will be interpreting this is the regression Herschel-Berkeley. I was telling the model and as well as the experiment. This both thing will come here. So this is the regression and this is the flow curve, right? I am switching it up. So you see, this is only for the data. What is that? Your shear stress versus shear rate. This is the basic thing, okay. And as sir told, a viscoelastic product will not have a constant viscosity, right? Viscoelastic, which is completely ideal in nature, it will have constant viscosity, but it's viscoelastic in nature, so it will not have constant. You see a different is viscosity. You can take average value, but the thing is that the main mechanism that you can't get a constant value, right?
Sir, I have one question. That
Yes.
since mayonnaise is a plastic fluid, so in the graph, for pseudoplastic fluids, there is no yield stress. Like there is no town out. So why here it's showing that it's the graph is starting
No,
from.
that is the yield stress only. That is the yield stress. Some things are there won't be any yield stress. Like I am telling you, viscoelastic, right? If you are taking water and you are pouring, okay, so it has its own strength. That's why it elastic in nature, right? So this is the minimum thing. After that, flow is happening.
Sir, but mayonnaise is a pseudoplastic fluid.
Pseudoplastic.
Yes, sir has discussed
yes.
that mayonnaise is a pseudoplastic fluid, and for pseudoplastic fluids there is no yield stress. That town out is equals to
No.
zero.
I don't know about the pseudoplastic yield stress, but it will give you yield stress. Yield stress means the thing is that whatever you are telling the pseudoplastic, it's okay, it will be in general, but you are taking some ketchup, you are taking some mayonnaise. You see this mayonnaise, if I am pouring on my palm, it will not going. It will, if I am doing like this, also it will not coming down. You have to apply some stress. So the stress at the point where the breaking down will be happening, so it will be flowing. So that is the yield stress. And you from the experiment you are getting the thing. Like as sir told, people are writing something, but you are doing something, literature. But here the experiment is going on. This is the yield stress, right? So this is the thing. The liquids are there. Those who are very liquid in nature, you won't get any yield stress, right? But it is, you see, viscoelastic in nature. Okay. So after certain point, when you will overcome the resistance of this mayonnaise molecule, then it will deform. And this is the curve between shear stress and shear rate. And you see, I showed you, this is the regression. Okay, regression. This is the model data is fitted, and this is the flow curve data. And same for another graph is there. This viscosity versus shear rate, right? You see, it's decreasing. In the morning, in the lecture, sir was telling it is decreasing with increasing the shear rate, right? It's not zero, because the graph is the plot, it is showing by a circular ball, so that's why it's showing, but it's not accurately zero, right? If you are taking the cursor here, it will show some values, right? So this is the basic case, like viscosity versus shear rate and shear stress versus shear rate. Okay, so Now this Herschel-Berkeley, you see also in this yeah, this is the model data. Okay, model means Herschel-Berkeley model, you are getting the curve between viscosity and shear rate, right? And one thing, whenever you will be taking the data, in the table, see in the flow curve, it is the data are there. So data it is the flow curve only. This is the experimental value, right? And this is the model value. Whenever you are going to draw the curve on origin or anything, you will get the value of AB, all the constant, and of this and you will tell. Another thing is shear thinning, because the shear thinning also you can get it from the Herschel-Berkeley, but you see the thing is that the shear thinning viscosity is decreasing. Okay, so this is the shear thinning behavior of the material. So now the thing is that after the test is completed, so we have to, this is the basic test, we have to raise the plate. Okay, so now it will go to upward position. You can see here 60 mm is set, means it will go up to 60 mm. You can tell why it is not going to up to that. We can set it that, but it is not desirable, right? We have to add the minimum space. In between that, our hands will go and we will add some sample. That is the minimum space. So this is the thing. You see, after this operation is happening, how is the structure like? Completely, it is applying. Yes. It's not like it is in symmetry, right? The branches of a tree. So in this way the operation happens. So I am telling another thing, like it will take time, another lectures is there, but I will show you one graph of the mayonnaise. What is happening here? This is the flow curve test, this is the basic test. And another thing is that I am showing you an amplitude sweep. You might have listened. See, this is the amplitude sweep, right? And what you are going to study now, I think sir will tell you the dynamic rheology. Okay, the dynamic rheology is that one thing is that here you know this G prime and G double prime. So this G double prime is the loss modulus. I am giving you some brief, and that was another experiment. This flow curve, you get the idea of shear stress and shear strain and the viscosity, right? And this is for the amplitude sweep. Amplitude sweep and frequency sweep are coming under dynamic rheology. Okay, sweep means what is a range. We are doing sweeping, so there is a range. So amplitude sweep means we are doing a frequency sweep, means under different frequency we are applying, and this amplitude sweep, what will get this linear viscoelastic range, right? You see, this is loss modulus G double prime and this storage modulus G prime. You remember this storage modulus G prime denotes to elastic nature, and this loss modulus denotes to viscous nature, because whenever you are putting some toothpaste inside the packet, it stays as it is, right? So that is at the time of storage, the elastic nature is more as compared to viscous nature. So that is G prime is higher, and in G double prime the viscous, whenever we are applying stress, it starts to flow, like we are pouring, we are pressing to take it out. So that is we are applying stress, so it tends to flow. At what point it is coming outside, that is the yield point, right? For that instance. So here the thing is that this loss modulus and storage modulus, it's not exactly stress modulus. Sir told you we are not directly talking about stress. This is modulus, right? Modulus means stress versus strain. So here is stress versus shear stress rate, strain rate. So the thing is that here the combination of storage modulus and loss modulus will be there, because it is viscoelastic in nature. So what this graph denotes, you see the graph actually went on to some point, and after that some point crossover happens. What I am telling you, this curve is between G prime, G double prime versus shear stress. You are applying shear stress. So what happened? You think the thing went on parallelly. Here it went on parallelly. At some point crossover happens. What is that crossover? You see here the value remains constant. What is this? This G prime, and here the G double prime value remains constant. So this G prime, why G prime is higher than G double prime? Anyone can tell? G prime is higher than G double prime. Viscoelastic solid. I told you this G prime is viscoelastic storage modulus, it is elastic in nature, and G double prime is viscous in nature. So here in our sample more elasticity is there, so this value is higher as compared to this G double prime. So what is happening, we are applying shear stress. At what point with the application of shear stress the sample needs to resist this shear stress. So till here the point is constant, like the value of G prime and G double prime is constant, that means the sample can bear till now, right? After that there crossover is happening, you see the G double prime is decreasing and the G double prime is decreasing and the G prime is also double prime is decreasing. So it's decreasing means what is happening, we are applying, this is storage modulus, we are applying the stress, though due to the application of stress the storage modulus is getting decreased and the viscosity nature of the product is dominating the elastic nature. That's why the G double prime is decreasing and G prime is decreasing, and the point till which both the things are constant, we can tell linear viscoelastic rate, right? This is linear, the thing is viscoelastic and this is the linear, okay? So this is the linear viscoelastic range. After that it is decreasing, it is not linear. So this amplitude sweep will get G prime, G double prime versus shear stress, and you can see the linear viscoelastic range, so under different shear stress, right? So the same thing you can also see different shear stress, you got it, and for different shear strain, you see for different shear strain percentage you will get also G prime, G double prime and the linear viscoelastic range, okay? So you see at some certain point when the linear region is over, it is getting decrease the values, right? So this is the basic thing like flow curve, and also this is the amplitude sweep, and sir will teach you now in the lecture this dynamic viscosity, this G prime, G double prime things will come, and I have given you some brief idea.